So today I'll be presenting on constructing a Faraday Force Magnetometer. And I'd like to thank the Department of Energy and NSF for providing funding. So what is a Faraday Force Magnetometer? Well, it's a device designed for measuring magnetization of different materials. And the model we're going to be talking about today was designed off for the Blaster et al. Paper. And it was designed to fit in a commercial dilution refrigerator, mounted on a cold finger, and to fit in a volume 2 centimeters cubed. The resolution of the magnetometer is 10 to the negative 4 EMU, and the previous design was tested down to 100 millikelvin and 14 Tesla magnetic fields. And our experiment will hope to probe 50 millikelvin region up to about 11 Tesla. And over on the right-hand side here, I have an Autodesk Fusion 360 rendering of the magnetometer that we built. And in here, we imported the schematics of each piece, and then I ran a rendering program to actually create the image that you see in front of you. So why use a Faraday Force Magnetometer? Well, it's a good question because there's already other existing magnetometry methods that are very precise and sensitive, such as VSM and squid techniques. And they can be really good, but the problem is that they require mechanical motion for operation. And this really is unacceptable when you're dealing with temperatures below 2K, because this just creates heat and basically creates noise. And so the Faraday Force Magnetometer is the easiest and best magnetometer to use when you want to go below 1K. And now some modern advancements to the Faraday Force Magnetometer allow for three-leg design, which allows for stabilization of torque components of magnetization, and also inhomogeneity in the externally applied magnetic field and anisotropies in materials as well. And you can see that the bottom left-hand corner is the three-legged design. And on the right-hand side, you have a picture here of different magnetometers and their sensitivity and resolution. And so you can see the Hall probes, and you can see here squid sensors, and the orange bar here highlights the sensitivity of Faraday Force magnetometers, and the most sensitive region on the bottom shows the sensitivity of fiber optic resonant magnetometry Faraday Force magnetometer setups, which are the most advanced type. That's not what we're going to be talking about today. So how does the Faraday Force Magnetometer work? Well, the idea is that you have some externally applied magnetic field, which I show here on the right-hand side is blue arrows. And what you're going to do is you're going to apply this magnetic field, which creates a magnetization on the sample, which is attached right here, as you can see. And the idea is that the sample isn't going to feel the homogeneous magnetic field because it only feels the gradient of B. So you have this magnetic field which creates magnetization on the sample, but then you are applying current, a plus and minus current, to two solenoids or inductors, and you're going to be creating a grad V field. And the idea is that you can measure this, and that it's going to be proportional to some deflection of the cantilevers, which are modeled as, and they're going to be modeled as parallel plate capacitors. And so you're going to have this, and then from that you can measure a change in the capacitance, and now you have capacitance meters that can measure down to 10 to the negative 18 farads. So you can get really precise measurements on this, and then you can back calculate magnetization. And the really important thing to know here is that you're actively controlling this magnetic field gradient, which really allows for precise measurements of magnetization and allows for this to be unaffected by inhomogeneity of the magnetic field and also of sample anisotropies. So here I show some pictures of the finished Faraday Force magnetometer. You can see the quarter for scale, the 2 centimeter by 2 centimeter area on the bottom. And you can see here the coils and the parallel plate capacitor. And I'll be talking more about this. So once you have it built, the idea is you're going to be mounting it onto a dilution refrigerator. In our case, we have a Kelvinox MX100. And you take it and you mount it onto the dilution refrigerator. It actually gets mounted onto the cold finger, and precisely it's going to get mounted right there. So next I want to talk about the system tests and future steps, because at this point we've built the magnetometer, and what's left now is to test it and to get the systems working and making sure that they're working as we expect them to. So steps are now to cool down the dilution refrigerator with the mounted magnetometer and obtain background subtraction data, and then to make sure that systems are all working as planned. That's where we are right now. And next, you want to cool down the dilution refrigerator with a mounted sample and obtain magnetization data for cesium chloride, which is the sample we're most interested in studying currently. And then after that, what's next is obtain PPMS data of your sample, such as cesium chloride, at higher temperatures. And what happens then is, so you can do that with the existing setup, and then you match that to other setups, such as with PPMS, and you can then create some accurate absolute magnetization calibration, which is important because you can't, when you put the sample onto the Faraday Force Magnetometer, you can't accurately put it in the exact spot every time, so you need to have calibration for each one. And so here you have the setup. You can see the Faraday, the capacitance bridge, which can measure down to 10 to the negative 18 farads. You have external current sources for the magnetic field and for the inductors, and the dilution refrigerator gets mounted on the the magnetometer gets mounted on the dilution refrigerator, which gets brought into the cryogenic systems and cooled down. And here's the actual systems over in the lab. And in the right-hand top corner, we have the actual sample, cesium chloride. So here, I want to show you guys what the data is actually going to look like. Well, this is from the Blosser et al. Paper, but our setup is going to be somewhat similar. So in the x-axis, you're going to have field in, you could say Tesla or whatever magnetic parameter you want. And then in the y-axis, you're going to have magnetization. And so you're going to be able to create some plot here. And then the idea is that you can test at different isotherms what this magnetization test field relation is. And this allows you to study phase transitions of different quantum materials. And this is what we're interested in studying. So next, I want to talk about some major challenges. It seems easy just to have a blueprint, but actually building this thing is really challenging. The solenoids are at 900 turns, 450 times 2 solenoids, and this wire is 2.5 mil. So it's 0.064 millimeter diameter, and a human hair is 0.075 millimeter diameter. So it's smaller than human hair, and it breaks just as easily. So it's really hard to wind these things, and it takes a very long time. And other difficulties are in creating other things, such as the coil rack, which you see down here in the left-hand bottom. And you can see that it's got a 0.1 millimeter thickness at this point. So, I mean, this is really challenging to machine. We started trying to make it with a StyCast 2850 epoxy, and when we were trying to dry it kept cracking, and there was no way for it to settle. So we ended up having to transition to a KLF material and using an extractive approach. We cut away the material we didn't want, and this worked, but it was really a challenge for us. I want to stress that this thing is not easy to make, and that's one of the hardships of making it. We've actually been working now on creating this thing for about a year. So in between the fabrication of parts and the hardware setup, and we had to do some dilution refrigerator upgrades, such as replacing thermocouples and things like this. And meanwhile, I'm taking graduate courses, so it's been a struggle, and it might seem easy to build this thing, but it's not. But I mean, in conclusion, it's still a really good magnetometer, and it can be really sensitive. And you want a Faraday Force Magnetometer setup for systems below 1K, because really the sensitivity is the best for Faraday Force magnetometers at this range compared to other magnetometers. And what's next is to create some automation process for sweeping the magnetic field at various temperatures, and then to conduct our first real tests on cesium chloride, which we're really excited to begin. So if there's any questions, I know this is an online video, so feel free to email me at donovandavino@brown.edu, and I'll be happy to get back to you with any questions you guys have. So thank you very much.